Hi, in this lecture we will see what vectors are and what are the basic operations that we can perform on vectors. Okay, so let's start. So in matrices also we have seen this concept, the concept of scalars and then vector and matrices, right? So what are scalars? Let's start with scalars. A scalar is a quantity with only magnitude. It only has a value. It has a magnitude. It does not have a direction. Right? A scalar is a single value. Right? Any number which you can think of, that is a scalar. So for example, temperature, mass. Like temperature generally does not have any direction, or mass does not have a direction. Right? Like they are just values, constant values, and they are scalars. For example, if I say an apple is 5 kg, then that 5 is a scalar. Okay. And on the contrary, vectors will have a magnitude and a direction both. Okay, so they will have a magnitude, which means a value associated with them, and a direction like a particular vector is of these many units long and it is in this particular direction. Okay, so a vector is a quantity with both magnitude and direction, which means displacement and velocity. If you see the analogy of a vector in science, right, in physics, you can say, like, you can see, right, like any object can have a certain displacement and it can move with a certain velocity, and that can be represented as a vector. Okay, so don't worry about that too much. Like, just think of vectors as any quantity which has a magnitude and a direction associated with it. So in 2 dimensions it is very easy to visualize a vector, because let's say you have a vector which is like 3 units in the x-axis and 4 units in the y-axis. So this is how the vector will look like. It is essentially 3 units in the x-axis and 4 units in the y-axis. So this is the vector we are talking about. Okay, so the vector which is drawn here, this is the vector we are talking about. Okay, and it is denoted by 3, 4. So this is a vector in 2 dimensions. So the number of dimensions in which a particular vector belongs is also the number of components the vector will have. See, this particular vector has 2 components, 3 and 4. Which means this particular vector belongs to 2-dimensional space. 2 dimension means this board, right? Like, which has an x-axis and a y-axis. A vector can have a single dimension as well, a single component. Let's say this is also a vector. It is a vector represented in a 1-dimensional space, like this. This is a 1-dimensional space, a single axis, right? And in the single axis you can have a vector 5 like this, or you can have a vector -3 like this, right, and so on. So here all the vectors will just have a single direction, okay, which is possible, and this is a single dimensional space, and this is how the vectors will be represented using a single component. In 2 dimensions the vectors will have 2 components. In 3 dimensions vector will have 3 components, x-axis, y-axis and z-axis. Okay, and hence, like, a particular vector can have any number of dimensions, any number of components, but beyond 3 components we will not be able to visualize it. Okay, because our world is 3-dimensional and we cannot visualize like objects or vectors which are having more than 3 dimensions. But vectors can exist and they can have any number of dimensions. Okay, cool. And how do we denote the component in each of the axes? We denote it using I cap, j cap, k cap and so on. Okay, so what does it mean? So here we have a vector which is 3 units in the x-axis, and 4 units in the y-axis, right? So we denote this vector either using this component, like using components 3 and 4, or we can denote it like this: 3 I cap plus 4 j cap. Now what I cap and j cap mean, we will see in the next slide. We will see later what I cap essentially means and what j cap essentially means. But this particular vector essentially means 3 units in the x-axis and 4 units in the y-axis. You can think of it right now this way. And if you have and this particular vector, let's say 5, it is in a one-dimensional space. Okay, only 1D, and this can be represented as 5 I cap. We don't have any j cap. If you are representing in 1 dimension, you will just have 5 I cap. Here you will have I cap and j cap both, and you can have a vector with 3 dimensions as well. Let's say 1, 2, 3. It has 3 components, so it is in 3-dimensional space, and you can write it also as 1 I cap, which means just I cap plus 2 j cap plus 3 k cap. Okay, so which means it is in 1 unit in x direction, 2 units in y direction and 3 units in z direction. Okay, so this is how vectors look like. They have a magnitude and a direction. Okay, let's look at types of vectors. So now vector can be represented in matrix notation. Okay, any vector. So let us say there is a vector with 3 components, 1 comma 2 comma 3. Okay, or let's say there are 3 components and the values are 5 comma minus 7 and 6. So the component in x direction is 5, y direction is minus 7 and z direction is 6. You can call this vector like this, you can write it like this as well, 5 I cap plus 7 j cap, sorry, minus 7 j cap. Okay, vector v is 5 I cap minus 7 j cap plus 6 k cap. Okay, this is the vector. Now you can represent the same vector in matrix notation using a row vector or a column vector. Both are okay. So you can write it like this. Let's say v is a vector. Then generally when you're writing in matrix notation, bold letter is used. Bold letter v. So bold letter, small and bold. Small letter and bold letter v is, you can write it like this, 5 minus 7 6. So here I have used a row vector to represent a vector, row matrix to represent a vector, and you can do that. You can use a it will be a 1 cross 3 matrix, right? There is only one row and there are 3 columns. So it is a row matrix. So you can use a row matrix to represent a vector, and this type of vector is called a row vector. If you are using a row matrix, then you will call it a row vector. And similarly, you can create a column vector as well. Column vector means you are just representing a vector. You are just representing a vector using a column matrix. Okay. So you can write it like this as well, 5 minus 7 and 6. And it is a 3 cross 1 matrix now. So if you are using a column matrix to represent a vector, it is called a column vector. If you are using a row matrix to represent a vector, it is called a row vector. And now any vector can have all its component as 0 as well, and that is called a 0 vector. 0 vector is essentially what? A vector which has all its components as 0. However many components it has, it doesn't matter. All the components must be 0, and that will be a 0 vector. Now notice a fact that the 0 vector in one dimension, is different from the 0 vector in 2 dimensions, and it is different from the 0 vector in 3 dimensions, and so on. They are all different. They all have the magnitude of 0. We will see this point. They all have a magnitude of 0, but still they are all different. For 2 vectors to be same, their components, their number of components or the dimension should also be equal. Then only the vectors are same. So if the dimension or the number of components in vectors are different, the vectors will be different. It doesn't matter if their value is 0 or not. Okay. So this is a different vector. The dimension itself is different. It is represented in a one-dimensional space, and it is just represented like this. This is the vector. Okay. There is no magnitude. And this particular vector will be represented like x-axis, and this is y-axis, and this particular point is the vector itself. Okay, so it is 0 in x direction and 0 in y direction, and this particular vector will be looking like x direction, y direction, and z direction, and it is a vector in this space. So the space or the dimension in which these vectors are present itself is different. They all represent the origin only, but still these vectors are different. Okay, and this is how 0 vector looks like. Okay, so row vector we have, which is represented using a row matrix. Column vector we have, which is represented using a column matrix. And 0 vector means all the elements of this particular matrix are 0. Okay, now let's see how do we denote a vector. Okay, right, like how do we write a particular vector in like mathematics. So there are multiple notations. First is bold lowercase letter, which means it will look bold. It will look different from other characters. Like if you're writing a normal A, it is different. But if you're writing bold A, it will be bold. Okay, and they always use lowercase character for vectors. Capital letters are used for matrices, small letters are used for vectors, and you can just have a bold character, then it will be a vector. The other convention is arrow notation. Arrow notation is better because it is very clear that it is a vector now. So you just add a vector like arrow on the top of it, and now this will be a vector. So you can either have a bold character or an arrow on the top. And now how do we denote the components of any vector? You can write the components of a vector using round brackets like this. You can write it like this. Let's say the vector has 3 dimensions. It is in 3-dimensional space, or it has 3 components. So you can write it like this, 5, 6, 7 in round brackets. So implicitly this will be in the x direction, this in the y direction, and it is in the z direction. So you can write the components like this. Or you can write the components using I cap, j cap notation, 5 I cap plus 6 j cap and 7 k cap. What I cap, j cap and k cap is, we will know, okay, very shortly. So you can write it like this as well, or you can write it using a row vector or using a column vector, okay, anything is fine. Okay, so you can denote a vector, like the components of a vector, in any of these ways, using like the round brackets, or I cap, j cap, k cap, or using a row vector, or using a column vector. Okay, now I told you every vector has a magnitude and a direction. It has a magnitude and a direction. So the magnitude of any vector is denoted, the formula for magnitude for any vector is square root of vx square plus vy square plus vz square if it has three components. If it has three components, we can write it as the x component square plus y component square plus z component square and square root of all of that. In general, the magnitude, let's say a particular vector has k components. Okay, a particular vector has k components. Let's say v1, v2, v3 and so on, vk. Okay, it has k components. Then the magnitude of this vector will be given by, this is how we denote the magnitude. Magnitude or the value, which means the length. Magnitude is also the length of a vector. Magnitude is also the length of the vector. So magnitude or the length of a vector is denoted using double bar. Why double bar? Because it is actually also the L2 norm of the vector. It is also the L2 norm. L2 norm and magnitude are both same things. What is L2 norm? We will see in the next lecture. L1 norm, L2 norm, L3 norm. There are actually all types of norms. But the magnitude of any vector is just the L2 norm, and that's why we use two bars. Okay. So magnitude of any vector is what? You just take squares of all their components and add them. Take the squares of all the components and add them, and at the end you take the square root of this value. So if if a vector has only one component, let's say a particular vector has only one component in a one-dimensional space, so the magnitude of this vector will be 5 square root, which is nothing but 5 only. And you can see like the length of this vector is 5 units only, right? Because it is like, this is the x-axis and this is the vector we are talking about. This is the vector we are talking about, right? So the length of this particular vector is 5 units, which is correct. Now, if it has two components, let's say a particular vector now has two components. So let us write it here. Let's say 3 and 4. Okay, it has two components, 3 units in x and 4 units in y. So this will be denoted like this: x, y. It is 3 units in x and 4 units in y. So this is the vector we are talking about. So what is the length of this vector? You can very easily calculate it using the Pythagoras theorem as well. See, this length is 3 and this length is 4. So this length will be hypotenuse, is perpendicular square plus base square under root, right? And that's the same thing we are doing here as well. So the norm of this vector or the magnitude of this vector or the length of this vector is 3 square plus 4 square root, which is 5 units. And we can check that the length of this vector is 5 units. And same thing will happen in 3 dimensions, 4 dimensions, 5 dimensions and so on. This is the general formula. Okay. So let's see an example on this. An example is, you have to find the magnitude of a vector which has two components, 7 and minus 24. So if I try to draw this vector, it will look something like this. In x-axis it is 7 units and in y-axis it is minus 24 units. So somewhere here it will lie. This is the point and this is the vector. And we want to compute the length of this particular vector. So you can see like this is 24 units and this is 7 units. So again you can use the Pythagoras theorem or you can use the direct formula. The magnitude of the vector P is, just you take the square of every component and you add them up and then you take the square root. So this particular is 49 plus 24 square, right? It is like the square root of 625, which is 25. So the magnitude, these are some of the standard values which you will remember slowly. Like for 3 and 4 the magnitude comes out to be 5, for 7 and 24 it comes out to be 25. But yeah, you can calculate it, okay, like this. So the magnitude or the length of this particular line or this particular vector is 25 units, okay. So this is how you can compute the magnitude of any vector. So throughout this course on linear algebra, we will be seeing some hands-on like vector drawing as well. So there are a lot of graphing calculators or graphing tools available online. We will be using Desmos. So here in this tool, like you will get a 2D plane or 3D also if you require, and we can visualize vectors. Okay. So what I did is, like, we just saw a vector 7 comma minus 24. So it's a vector starting at origin 0 comma 0, and it goes to its x component is 7 and y component is minus 24. Right. So I just like created a list containing 2 points like 7 and minus 24. Then I created a vector. So in like here, you can actually draw lines, and to draw multiple like you can join multiple points and create like line like this, and you just need to give a list containing like all like details of all these points. So here like using round brackets I can give like multiple such points. So what I did was I like created these 2 points 0 comma 0 and 7 comma minus 24. So like I wanted to make it dynamic, so that when I change the point here, the line also changes. So if I just want to visualize it, I just click this button and I can see this line, this vector basically. So here I can see like 2 points 0 comma 0 and 7 comma minus 24, and there will be line. So like basically it's a vector for us, right? So it's a vector which has an x component of 7 and y component of minus 24. Then to create like to calculate magnitude, I just defined the function magnitude. Like magnitude of a vector containing 2 components will be square root of a square plus b square, and this is like just like where I want to display the magnitude. I want to display the magnitude on the middle of the line, so I just created a point and gave it a label. Magnitude is this much, and the magnitude of the vector p is like I just passed in the function m, I just passed p1 and p2, which means it will just calculate the magnitude with the x component 7 and y component minus 24. Don't worry how Desmos works. You can play around with the software and you'll like get to know. I can share the link to this particular calculator with you guys as well, so like you can just play around with it directly. So the idea is I just like now I'm just seeing the vector and the magnitude both. Okay, so you can see here according to the formula square root of a square plus b square, or square root of the x component square plus y component square, I can see the magnitude of this vector here. Now if I change the vector, like let's say instead of like I'm changing the x and y component, instead of 7 comma minus 24 I made it 7 comma plus 24. So for this vector also the magnitude or the length remains same, it is 25. If I change it to 7 comma 4, now the magnitude changes, as you can see. So its magnitude is 8.06 now. And if I make it 3 comma 4, so if the x component is 3 and y component is 4, this is the vector that we are talking about, and its magnitude is 5. So we will keep on seeing this software, and like as we learn more concepts like addition, subtraction, we will see it visually on the software. Okay, now let's look at coordinate systems. Coordinate system means again like the same axis that we have. So in 2D space, we represent it like this, x-axis and y-axis. In 3D space, we cannot represent it on a 2D plane, obviously, because the z direction will be like this, going like outwards. Okay, but I can like represent it like this. So this is the z direction. Okay, and for every point we can say how much is it in the x, how much component it has in the x-axis, how much component it has in the y-axis, and how much component it has in the z-axis. So let's say if we have a vector here, let's say in 2D space like this, so we can say that let's say this is 5 units and this is minus 4 units. Then this particular point is 5 I cap minus 4 j cap, which means 5 units in x-axis and minus 4 units in y-axis. Similarly, if we have a point in 3D space somewhere here, and it has like x component as 3 and y component as minus 2 and z component as 2, then this particular vector, okay, it looks like a 2D vector, but it is actually a 3D vector. It lies somewhere around here. Okay, and this particular vector can be represented as 3 I cap plus minus 2 j cap plus 2 k cap. Okay, which means it is 3 units in x-axis, minus 2 units in y-axis, and 2 units in z-axis. Okay, so this is how we can represent vectors in Cartesian plane. Cartesian plane means this, x-axis, y-axis, and z-axis. So this is how you can represent them. Again, y I cap, y j cap, we will see after scalar multiplication. Okay, and the other way of writing a vector in 2D space is using polar coordinates. Only if a vector has 2 components and you are representing it in Cartesian plane, which means like x-axis and y-axis, you can represent it using r and theta as well, which means the length and the angle it creates on x-axis, on the positive x-axis. Okay, so this is only for 2D space, two-dimensional vectors. For two-dimensional vectors, you can represent them using polar coordinates as well, which means they will have a magnitude. The magnitude will be denoted using r, which means the length, and theta is the angle it creates from the positive x-axis. So what does it mean? Like, let's say we have, this is the x-axis, this is the y-axis, and I am saying we have a vector of length r, okay, and let's say r is 5, it has a length of 5, and this is how it is denoted, okay, and this is the angle it creates with the positive x-axis, this is the angle it creates with the positive x-axis, theta, okay. And now let us say the value of theta is also given. Let's say theta is given to be 53 degrees. Theta is given to be 53 degrees. So what will happen? So if you know a little bit of trigonometry, the projection of this vector on x-axis, so this particular length will be r times cos theta, r times cos of theta, and this particular length on y-axis will be r times sin theta. So if I am representing a particular vector you like this, 5, 53 degrees, 5, 53 degrees, then the same vector can be written as 5 cos 53 degrees, 5 sin 53 degrees. Like this, 5 cos 53 degrees, 5 sin 53 degrees, because x component is this much and y component is this much. So if you are writing any vector in polar coordinates means that the dimension or the value, the magnitude and the angle it creates with the positive x-axis, okay. So then its x component will be this much and its y component will be this much. So here 5 into cos 53 degree is 3 by 5, okay, and here 5 sin 53, so sin 53 degree is 4 by 5. So here the x component will become 3 and the y component will become 4. So this is nothing but 3, 4. So you can say that here the x component is 3 units in length and y component is 4 units in length. So this is also the vector 3i cap plus 4j cap, okay. So this is another way of writing a vector in polar coordinates, and only 2D vectors are represented like this. And for these vectors you can actually compute its x value and y value both, which means like the x component and the y component both. So this is another way of writing or denoting a vector in polar coordinates. Cool. So here we have an example. In polar coordinates, convert r is equal to 5, theta is equal to 53.13 degrees to Cartesian coordinates. We just solved the same example. R is 5 and theta is 53.13 degrees. So the x coordinate will be r cos theta and the y component will be r sin theta. So r cos theta is 5 into cos of 53 degrees, which is 3 by 5, and r sin theta is sine of 53 degrees, which is 4 by 5. So this is 3 and this is 4. So the if you want to convert this particular polar coordinates to Cartesian coordinates, the Cartesian coordinates will become 3i cap plus 4j cap. Okay, this is the answer. Cool. Okay, moving on. Now let us look at vector addition. How do we add two vectors? Okay, so we will look at the geometric interpretation as well on the software, and we will look at the mathematical formula both. So how do we add two vectors? Firstly, let me give you the general formula. So let's say there are two vectors. A vector is having k components. It is having k components, which means it is in k dimensional space. And vector b is also in k dimensional space, which means let's say the components are b1, b2 and so on bk. So they are both in k dimensional space, okay. And we generally write it like this as well, like it belongs to real number k, it belongs to also real number k, which means they are both in k dimensional space and the components are all real numbers, okay. So first concept, you can add two vectors or subtract two vectors only if their dimensions are equal. It is the exact same thing that we saw in matrices as well. You can add two matrices or subtract two matrices only if their order is same, the number of rows and columns are same. Same thing happens here. You can add two vectors, subtract two vectors only if they are in the same dimensions. If they are in different dimensions, you cannot do any operations on them. Addition, subtraction is not allowed. So here they are in the same dimensional space. How do we add them? Very simple, just like vector addition. You just add them component by component. So the first x-axis component will be added, a1 plus b1. Then the y-axis component will be added, then the z-axis component will be added, and so on. For every dimension, we will just add the components element by element. That's all. This is the addition of these two vectors. Okay, so if you have a vector, let's say with 4 components, 1, -1, 4 and 7, and we have another vector with components 2, 1, 3 and 4, then their addition will be another vector in the same space, which is the 4-dimensional space, and its component will be 1 plus 2 is 3, then -1 plus 1 is 0, then 4 plus 3 is 7, and then 7 plus 4 is 11. This is the vector, okay, in 4-dimensional space. Again, it is very difficult to visualize it, but yeah, this is the vector. Cool. So the formula is like if a vector has 3 let's say dimensions, it is in 3-dimensional space, it has 3 components. Vector A has 3 components, ax, ay and az in x, y and z, and vector B has also 3 components, bx, by and bz. Then their addition will be ax plus bx, ay plus by. So you just add the x components, y components and z components, and you'll get the addition of these two vectors. And here is an example. If the vector is in 2D space 3, 4, and another vector is another 2D space in the same 2D space 1, 2, then their addition will be 3 plus 1, 4 plus 2, which is the vector 4, 6. Now there is a geometrical interpretation of it as well. Like how does the vector actually shift? Like if you have a vector of 3 units in x and 4 units in y, and if you have another vector which is 1 unit in x and 2 units in y, how do we add them and how do we get essentially this vector? This we will see on the software, okay, or the platform. Okay, now let's see addition of vectors on Desmos now. So firstly, we just in the example took two vectors. Vector A is 3i cap plus 4j cap. So I'll just draw this one. So this is the vector, right? 3i cap plus 4j cap. Now I'll draw the vector B. Vector B is 1i cap plus 2j cap. So this is the vector B. Okay. So this is vector A and this is vector B. Now what I did is I have actually created one more vector B2. B2 is what vector? B2 is the same vector as B only. It is the same vector as B only, but it is starting at the end point of vector A. It is starting at the end point of vector A. So this particular, like you can actually shift vectors. So this, I have actually shifted the same vector and I have drawn it using a dotted line here. If you see, it has the same angle and the same magnitude. Same angle, same magnitude, it is just shifted. Instead of starting at origin, it is now starting at the point where vector A was ending. The reason of it is, actually, like you can shift vectors, it doesn't matter, the vector remains same as long as the magnitude, like what is a vector? Vector has a magnitude and a direction. The magnitude and direction of this vector and this vector are exactly same. So they are the same vector. It's just the frame of reference. This vector like starts at origin and this vector starts at point 3, 4. So you can move the origin there, it doesn't matter. So it is essentially the same vector. Why did we do it? Because I wanted to show you the magic. Now when you calculate the vector S is what? Sum of A and B. So we already know how to calculate the sum of two vectors A and B, right? I just took the sum of the x coordinate and the sum of y coordinate, like the sum of the x components and the sum of y components. Like I defined S this way: A1 plus B1, A2 plus B2, which means I am just summing up the first values and the second value. So this is another vector S. So when I draw this vector S now, it is exactly this vector where this particular vector ends. It is exactly the vector where the entire vector ends. And this, like you can have any vector B, like it doesn't matter. Like let's say vector A remains same 3, 4. I change vector B to -1, 2. So this is the vector B -1, 2. And I have now drawn the same vector B -1, 2 here in the dotted line. So it is the same vector, same magnitude, same direction, but it is starting at ending point of vector A. So this is the vector now. And when you calculate the sum of these two, it is exactly the same vector which is ending here, like 2, 6. Right? So this is the geometrical interpretation of adding of two vectors. When you add two vectors, it is like just you take one vector and start the other vector at that point and like take that vector and wherever you end. that particular point is the addition of these two. Okay, so this is geometrical interpretation. We can try some more examples as well. Let's say if I make b, let's say 11 comma 2, it is fine. So b is 11 comma 2, and if we shift it, this is the dotted line, the vector b2, which is the dotted line, it is starting at this position, and their sum is this vector 14 comma 6. So 11 plus 3 is 14 and 4 plus 2 is 6. So if this is vector a, this is vector b, their sum is this. Okay, and we can do some other things as well, like we can actually make vector b in the same direction as vector a. Let's try that. If I make vector b in the same direction as vector a, so if I make vector b, let's say 6 comma 8, we can do that. So vector a is 3 comma 4, vector b is 6 comma 8, and vector their sum is also in the same direction. In this case it is 9 comma 12. Okay, and we can make the vector b, let's say 0 vector as well. That is also fine. If you make the vector be 0 vector, then vector a and vector, the sum vector remains like they are both the same vector. Okay, so these are like you can like play around with these vectors. So I'll share this like again the link of this thing with you, and you can like play around with vectors and check their sum. So this is how vector addition is performed. Like this is how actually vector addition is visualized. You can see like it this way. Okay, now let's look at vector subtraction. So again, just like addition, subtractions work the exact same way. You just have to subtract the components component by component. Okay, so again, like if you have a vector, let's say a vector in k-dimensional space, which is like a1, a2 and ak in k-dimensional space, and another vector b in which is also in k-dimensional space. Okay, then their subtraction, a vector minus b vector will be another vector in k-dimensional space. You can only subtract two vectors if they are in the same dimensional space, which means they have same number of components. So it will be a1 minus b1, a2 minus b2, and so on, ak minus bk. Okay, this is the vector. So if you have a vector, let's say in 4-dimensional space, 4, 1, minus 3 and 4, and another vector in 4-dimensional space, 0, 1, 5 and then minus 2, then their subtraction, a vector minus b vector will be another vector in 4-dimensional space. 4 minus 0 is 4, 1 minus 1 is 0, then minus 3 minus 5 is minus 8, and 4 minus minus 2 is 6. So this is the vector. Okay, this is how we do it. Now, and you can also write it this way. So like actually addition, like subtraction is nothing but adding the negative of the vector, So a vector minus b vector is nothing but a vector plus minus of b vector. Now minus of b vector is what? It is minus 1 times b vector. So you are just adding the negative of this vector to the vector a. Okay, negative means we will see like how do we multiply a scalar to a vector. It's very simple. You just have to multiply the same scalar to every component. Okay, so adding, like subtracting a vector is nothing but adding the negative of that vector to the previous vector. Okay, so this is how it works. And here is another example. Let's say if vector a is 3 comma 4 and vector b is 1 comma 2, then their subtraction will be 3 minus 1, which is 2, and 4 minus 2 is 2, so 2 comma 2. Okay, now we will see the geometric interpretation of it, how this particular subtraction actually happens. Okay, now let's see subtraction of two vectors. So again, like the example that we saw in class, like this is vector a. Vector a is 3 comma 4, which means its x component is 3 and y component is 4. And this is vector b. Vector b is x component 1 and y component 2. Okay, so now I have created another vector which is starting at this point, which is starting at the end of vector a, and it is minus b. So what is the vector minus b? Vector minus b will be minus 1 comma minus 2, something like this, right? And I have just like placed this entire vector at the like at the end of vector a. So this is what minus b will look like. This is what minus b vector is. So if we have to draw the directions, like it will look something like this. So this is vector a, this is vector b, and this is vector minus b, right? It will look like something like this. And hence I just shifted it here, like at the end of a. So this is vector minus b. So vector a minus b is what? Vector a minus b is a plus minus b. You are just adding minus b vector to a. So it will just end at this particular location, right? So let me show you. Like the vector a minus b is vector d for us. So this is the vector a minus b. So it will end at 2 comma 2. So if a is 3 comma 4, b is 1 comma 2, vector a minus b will look something like this. Now an interesting property is, if I start vector a minus b at the ending position of vector b, if I start the vector a minus b at the ending position of b, I told you like the reference point, the point at which you are starting a vector doesn't matter, just the magnitude and direction matters. So I can shift this vector. So if I shift this vector and I start it at the ending position of b, I land at a again. So I have drawn that vector is vector d2. This dotted vector, the vector d2 is the same vector a minus b, but it is now starting at b. So now this particular vector lands at vector a. This is beautiful, right? Like, let me explain what is going on here. Let me make the point a. Let me make vector a 3 comma 3 so that the diagram is like more understandable. So now what I did, I made vector a 3 comma 3. So this is the vector a. Okay. Okay, cool. Okay, cool. So this is vector a 3 comma 3. Okay, and vector b is what? 1 comma 2. So this is vector b. Okay, and sometimes these are also called vector oa. You can also call them vector oa and ob. If this is the point a, if this is point a 3 comma 3 and b is the point 1 comma 2 and o is the point origin, then you can also call the vector a as oa vector, because it is starting at origin and ending at point a. It is starting at origin and ending at point b. So you can call them OA and OB as well. Like, this is another notation in which you can write vectors, in which you are saying starting point and ending point. Generally speaking, if you are just writing a vector A like this 3 comma 3, you are always starting from origin. The frame of reference by default will be origin. That's why you can write it OA and OB as well. Okay. So this is what vector A and B are. Now the vector A vector minus B vector is like 3 minus 1 is 2 and 3 minus 2 is 1, 2 comma 1. So this is the vector a minus b. This is the vector a minus b. But if you just start this, the reference point, the starting point of this vector was also origin, right? The starting point was also origin. But if you just make the starting point as b, this particular vector a minus b ends at the point a. And this vector if you look at, what the starting point for this vector is b and the ending point is a. So this vector is called the vector ba vector. This particular vector is the vector ba vector, right? Starting point is b and the ending point is a. So this is not OA or OB, this is BA. BA means starting point is b and ending point is a. But this vector is nothing but essentially the subtraction. It is nothing but a vector minus b vector, right? I told you, like, the reference point again doesn't matter, like where you are starting doesn't matter. This is also a vector minus b vector. This is also a vector minus b vector. They are both same, right? It is just shifted. So the vector BA vector is a vector minus b vector, which is nothing but OA minus OB. Okay. So this is another identity. This is another way in which you can understand vector subtraction. The BA vector, the vector which is starting at B and ending at A, is nothing but a vector minus b vector. Okay. And if you don't understand it, it's completely okay. Like, understand, like, the more important part is this part. If vector a is this, like 3 comma 3, vector b is 1 comma 2, then their subtraction will be 2 minus 1. And the important identity to remember here is a vector minus b vector is like just you just have to subtract them element by element, or you can write it like this, is like a plus minus b vector. So you are just adding the minus b vector, which is this vector, to a. Okay, and you'll get a vector minus b vector. So this is how a minus b works. Now in the same plot you can add the summation as like the sum as well if you want. Like, the sum vector actually looked something like this. The green one, it was 4 comma 5, and it was actually adding b vector to a vector. So for that we drew this vector, right? So at a, if you draw a b vector on top of it, you'll land at a plus b. So this is a plus b and this is a minus b. Okay. And as you can see, there is no definitive relationship between the magnitudes or angles of these. Vector a had certain angle, vector b had certain angle with x-axis, a plus b has certain like some angle which is not related to a or b, and like a minus b also has some other angle. Okay, so there is no relation as such, but yeah, you can figure it out if you want to using like complex trigonometry, but we will not go there. Okay, so this is how vector vector addition and vector subtraction actually looks like on graphs. Okay, now let's look at scalar multiplication, which means how do we multiply a vector by a scalar. So multiplying a vector by a scalar means magnifying that particular vector by that amount. So let us say if we have a vector in x-axis and y-axis, we have like this is the vector. So let's say it is 2 units in x and 1 unit in y. Okay, so this particular vector can be represented like 2 comma 1. Its x component is 2 and y component is 1. Now if I say, let's say this is my vector a vector, okay, then 2 times of a vector will be what? Its what will happen, its direction will remain same. In the same direction, now it will be magnified by 2 times. So previously whatever its length was, now it will be magnified by 2 times. Okay, so both its components, since its direction remains same, both its components will increase by the same amount. So if it means that you just want to multiply 2 to the x component and multiply 2 to the y component, so it will become 4 comma 2 now. So now in the same direction, now the vector has become became 4 comma 2 like this. Okay, so now it will have the x component as 4 units and its y component will now become, okay, cool. So its y component will now become 2 units. Okay, so in the same direction, previously if the y component was 1, now it became 2, and previously if the x component was 2, it became 4. So it magnifies in each of the component by the same amount, and now the vector changes. Okay, so its direction remains same. If it was making an angle theta from the x-axis previously, now also it is making the same angle theta with the x-axis, but now it just got magnified by that amount. And this scalar need not be a number greater than 1 only. It can be a smaller number also. You can have half of a also. Half of a vector will be what? It is like multiplying both the components by half. So you are shrinking it. So then you will get a vector like this. So half of a vector will be half into 2 is 1 and half into 1 is half. So 1 comma half like this. So it will have one component in x-axis and half as the component in y-axis. Right? Still the angle remains same. And even this scalar can be negative also. So you can have minus 1 times a vector, which is also called the minus of a vector, will be what? You are multiplying minus 1 to both of them. So it will just become minus 2 comma minus 1. So this is the vector like now we are talking about the same angle, and now it will have the y component as minus 1 and it will have the x component as minus 2. So this is the vector minus of a. This is the minus of a vector. Okay. So this is how it happens. The angle will remain same. Either you will shrink it, you will expand it, or you will like change the direction of it like in the negative side. Okay. So both of them, but still the entire vector will keep on remaining. It will remain on the same line. It will have the same angle. It will not skip this line. Okay. If you are multiplying it by a scalar, this is how scalar multiplication works. So if it has 3 parts, 3 components, ax, ay, az, then k times vector a is k times ax, k times ay, and k times az. And you can actually generalize it to any number of dimensions. If a vector a has k components, a1, a2, ak, then if you are multiplying this particular vector by a scalar c times a vector will be c times a1, c times a2, c times ak. And like if this is in k dimensional space, the new vector is also in the same k dimensional space. Okay, so if let's say there is a vector a with 4 components, 4, 1, minus 3 and 0, and if you're multiplying this vector by let's say 5 times of this vector will be 20, 5, minus 15, 0. And similarly half of this vector, minus half of this vector will be minus half, like you will multiply every component by minus half. So you will get minus half into 4 is minus 2, then minus half into 1 is minus half, then minus half into 3 becomes 3 by 2, and 0 times minus half remains 0. So this is how the scalar multiplication works. Now I told you a concept. like any vector in Cartesian plane can be represented using I cap, j cap, k cap and so on. So now let's try to understand what I cap, j cap, k cap means. Okay, so to do that, let me explain you here. So firstly, let's understand one-dimensional space. If a vector is in one dimension, only x-axis is there. Okay, there is no y-axis or anything. Then a vector of unit length. A vector of unit length is called a unit vector. So any vector whose magnitude is 1 is called a unit vector. Any vector with a magnitude of 1 is called a unit vector. Okay. So in positive x direction, if I create a vector like this of length 1 and this is the vector. In one dimensional space I am creating it. So this is the vector with one component. This particular vector has one component 1 and it is in one dimensional space. So the length of this vector is what? The length of this vector is 1 and it is in positive x direction. So this particular vector, this particular unit vector in positive x direction is called the unit vector and it is denoted by standard term is I cap. This is called I cap. This vector is just I cap. Okay, and if right now we are denoting it in one dimensional space. Similarly, if you are working in two dimensional space, which has a y also and it has x also, then again a unit vector in positive x direction, a unit vector in positive x direction is this vector, right? It will have like x component as 1 and y component as 0. It will have x component as 1 and y component as 0. So this vector is called I cap vector. So by default I cap vector in two dimensional space will be 1, 0. So the I cap vector by definition in 2D space, if it has two components, is 1, 0. In 1D space it is just 1, but in 2D space we must have two components. So the x component will be 1 and y component will be 0, and you can check that it is a unit vector because the dimensions, or sorry, the magnitude of this vector will be 1 square plus 0 square under root, which is 1 only. Okay, so a unit vector in positive x direction is called the I cap vector, and similarly the unit vector in positive in y direction, in positive y direction is called the vector j cap. So the j cap vector is having 0 component in x and 1 component in y, and the magnitude of j cap is also 0 square plus 1 square under root, which is 1. So a unit vector in y direction is called the vector j cap. Now same thing will happen in 3 dimensions as well. In 3 dimension space, the vector I cap will be 1, 0, 0, which means x component will be 1. The vector j cap will be 0, 1, 0, its y component will be 1, and the vector k cap, the unit vector k cap is 0, 0, 1, which means its z component will be 1. And because of this property, by definition, this is how I cap, j cap and k cap are defined in different dimensions. Okay, in 1D space only I cap is defined, in 2D space I cap and j cap are defined, and in 3D space I cap, j cap and k cap, all three are defined. This is how we define these vectors, I cap, j cap and k cap. Now any vector can be represented as a combination of these vectors. It is a very interesting property. Okay, the claim is any vector in 2D space. 2D space means having two components, with two components. I can write it this way as well. With two components can be represented as a linear combination, of I cap and j cap. Later in the next module I will call these, like in the next module we will see all these things. This particular line actually contains the entire module 3 that we will see. We will see the word linear combination, we will see the term space, and that is why we will say that the vector I cap and j cap span the entire 2D space. So span and these terms we will see later, but right now let's try to understand what I'm trying to say. So if I have a vector, let's say in 2D space denoted by 7, minus 6, what does it mean? Think about it. Like now we will apply all the concepts that we have seen so far. Its x component is 7 units and its y component is minus 6 units. Its y component is minus 6 units. Okay, this is positive x, this is negative x, this is positive y, and this is negative y. This is the origin 0, 0. So this is the vector we are talking about, right? 7, minus 6. This is the vector v. Now I can write this vector as 7 times I cap minus 6 times j cap. Why? Because I cap is what? The vector I cap is what? We already know the vector I cap is a unit vector in positive x direction. This is I cap. Okay, and this is j cap. Okay, so I cap is 1, 0. We already know this. And the vector j cap is what? 0, 1. So this is the vector I cap, this is the vector j cap. Now if I compute this 7 times scalar multiplication of vector I cap. So this is the vector I cap having a unit length in positive x direction. If I magnify it by 7 times, I'll just get this vector. This is 7 I cap. This vector is 7 I cap. And the vector j cap is having a unit length in positive y direction. If I multiply it by minus 6, I'll get this vector. This is the vector minus 6 j cap. This is the vector 7 I cap, this is the vector minus 6 j cap. If I add these two vectors, if I add 7 I cap and minus 6 j cap, I'll get the vector v. That is why we are writing, like from the beginning of this lecture, we are writing I cap and j cap notation. This is what it means. I cap is a unit vector in x-axis, j cap is a unit vector in positive y-axis. You can multiply, like if any vector has any component in x-axis, you can just get it by multiplying that particular scalar by I cap, and same for the y-axis. Okay, so what is this vector? So 7 times this vector is 7, 0, this vector, and you can add, like this is like multiplying minus 6 to this vector, minus 6 to this vector, so you will get 0, minus 6. This is the vector minus 6 j cap, this is the vector 7 times I cap, and if we add these two vectors, we will get 7, minus 6, which is the desired vector v. And that is why we are writing it this way, I cap, j cap. Now I think it makes sense, right? And actually you can represent any vector in 2 dimensions like this, right? Using I cap and j cap. And we will have a beautiful term for it in the next lecture. What are the vectors I cap and j cap? We call it span, and we will see it in the next module. Okay. So this is how you can write, and same thing you can do for in one axis you can write any vector as just using I caps. In 2 dimensions you can write it using I cap and j cap, and in 3 dimensions you can represent any vector using I cap, j cap and k cap like this. Okay, this is what scalar multiplication does. Now let us say if you, here is another example. If you have a vector a 3, 4, and if you want to multiply it with 2, you will get 2 into 3, 2 into 4, and the new vector k times the vector a will be 6, 8. Okay, this will be 6, 8. Cool. So this is all about scalar multiplication. Okay, now let's see a few properties of vector operations. First is commutativity of addition. So just like matrices, vector addition is also commutative, which means vector a plus vector b will be equal to vector b plus vector a. And this is very normal, like even if you represent a vector using matrix, because like all the properties of matrices should hold for vectors as well. I can actually, like, to prove it very simply, you can say that okay, you can say that, let's say vector a is represented in a column vector, okay, as a row vector, let's say, like a1, a2, ak. This is a column vector, oh sorry, this is a row vector, okay, row vector containing k columns, so it is 1 cross k vector. And vector b is again represented as a row matrix like this, b1, b2, bk. It is another 1 cross k vector, right? So 1 cross k matrix. So they are both represented using row matrices. That's why they are row vectors, and hence we can add them. You can add a row vector to another row vector, and you will get a1 plus b1, a2 plus b2, and so on, ak plus bk as another row matrix 1 cross k. And even if you add b vector plus a vector, you will get the same matrix. You will get the same matrix b1 plus a1, b2 plus a2. Essentially, it's the same matrix, right? And since this property holds true for matrices, the same property will hold for vectors as well. So the same properties that we saw for matrix algebra will hold for vector algebra as well, because you can add them this way. And hence a plus b will be equal to b plus a. And for subtraction, we saw it was not true. vector A minus vector B will not be equal to vector B minus vector A, because for matrices also, matrix A minus B is not equal to B minus A. Actually, it is the negative of that. So same thing will happen. Commutativity of subtraction will not be there. I cannot say that A vector minus B vector will be equal to B vector minus A vector. No. Okay. It will be just the negative of that. Okay. Now associativity, again the same proof follows. Since the associativity hold true for matrices, the same associativity will hold for vector as well. The order in which you add vectors doesn't matter. A plus B plus C will be equal to A plus B plus C. In which order you add, it doesn't matter. And similarly, the distributive over scalar property K times A plus B will be equal to Ka plus Kb. So same property we have seen for matrices as well. K times matrix A plus matrix B will be equal to K times matrix A plus K times matrix B. And same property will hold for vector as well, because you can actually represent them as row matrices or column matrices, and the same property will hold true. So these are a few properties on vector operations. And actually, like, you can have more such properties as well. Like because of the same rule, you can say that we had the existence of identity element, right? So or additive identity. So you can add any vector with the 0 vector and you'll get the same vector back. It's just that the dimension must be same. So if this is a vector in 3 dimensions, if it has 3 components, if it belongs to 3 dimensions, this 0 vector is also belonging to 3 dimensions. And if you add it, you'll get the same vector back. The same property we had for matrices as well, right? And hence 0 vector is called the additive identity for any vector. And similarly, we can have multiplicative identity as well. So if you multiply 1, the scalar 1 with any vector, will get the same vector back. And hence the scalar 1 is the multiplicative identity. Okay. So same properties we have seen for matrices and they hold for vectors as well. Cool. Now let's see an example. If you have a vector u vector 1, 2, 3 and v vector 4, 5, 6, you have to find 2 times u vector and 3 times v vector. So 2 times of u vector will be 2 into 1, comma 2 into 2 and 2 into 3, which is 2, comma 4, comma 6, and then 3 times of v vector will be 3 times 4, 3 times 5, 3 times 6, which is 12, 15, 18. And if I add these two vectors, I'll get 2u plus 3v. This vector will be 2 plus 12 is 14. Then 4 plus 15 is 19. And then 6 plus 18 is 24. So this is the vector that we got. Okay, and all of them are in 3-dimensional space. So this is how you can solve that very easily. It's pretty simple. And you can solve it same thing using matrices as well. You can represent it using a column matrix also. So I can write like 2 times the column matrix 1, 2, 3. I am representing them as column vectors right now. So 2 times this plus 3 times this. I'll get the same matrix as a column matrix. I'll get 14, 19 and 24. Okay, so you can solve it using matrices, row matrix or column matrix. Okay, you'll get the same answer. Cool. So this was all about the basics of vector, how do we denote it and so on. In the next lecture we will see more concepts on vectors. Specifically the most important one is angle. How do we calculate the angle between two vectors or the angle a vector creates from the x-axis and so on. Okay. So thanks for watching this lecture. Let's meet in the next one. Bye bye.